In this video series, we're going to give some applications of residues. So earlier we introduced residues as just sort of this coefficient in Laurent series expansions, but we didn't explain why they were important. So this video will give some nice applications that will hopefully inspire you to be interested in the full residue theorem that we learn later after we get into all the details of complex line integrals. But for now, we're going to present what I'll call a baby residue theorem, which is the residue theorem on a circle. And I'll use that to do a case study of the function z over e to the z minus 1, and we'll use residues applied to this function to prove interesting formulas like the famous formula pi squared over 6 equals the sum of 1 over n squared. And then after that, we'll use residues to finally give a proof of the Lagrange inversion theorem, or the Lagrange inversion formula. I'm reminded of an old joke. Why was the complex analyst's dog named Koshi? And you'll have to wait till the end of this video to hear the answer to the joke. But first, let's get into what I'm calling the baby residue theorem. And it's really just the residue theorem on circles, and we'll do something more general later. But let's assume that we have a function f, which is meromorphic on a neighborhood of the closed disk of radius r centered at 0. And we want there to be no poles on the circle of radius r. Okay, and the conclusion is the complex line integral around that circle of radius r of just f dw over 2 pi I will just give me the sum of the residues of z1 through zn, which are just f's poles. So we're assuming that f is meromorphic on a neighborhood of the closed disk of radius r, so it can only have finitely many poles in this compact set because they cannot accumulate, or else this would force f to be constant or identically infinity. Let me just recall a little bit about residues. So the residue of f at zj, again, is you have to write out f's Laurent series centered at zj, and we're just pulling off the coefficient of z minus zj to the minus 1. This can also be computed by taking a small circle around zj, integrate around that circle of f dw over 2 pi I. So that's what residues were, and at the time that we introduced these, they didn't seem like anything special. But this residue theorem is very powerful. In order to prove this easy version of it, we need just the following lemma. Let's have the same setup as the theorem. So f meromorphic on a neighborhood of this closed disk with no poles on the boundary circle. We want to know how to compute these integrals, 1 over w minus zj to the n, integrated just with respect to dw 2 pi I. And I claim this is just 1 if n is 1, and 0 for n bigger than 1. Why is this? Well, you can view this as an instance of this formula for computing derivatives that we've had before. So our formula before for computing derivatives at a point was, let's see, the kth derivative at z0 divided by k factorial can be computed by doing a Cauchy integral, which was f of w over w minus z0 to the k plus 1. and this would be, let's say, on some disk of radius r that f is analytic on. So forget about the f from earlier temporarily. We had this derivative formula, and now I'm just going to apply it to the function 1. And I know that the derivative of 1 is, well, if I take any derivatives of 1, I'm going to get 0. So that's for k bigger than 0. But then if I don't take any derivatives, I'd just get 1 back. And so this is exactly what we're doing over here with just kind of a shift in the notation. So we do need this to prove the theorem, but this is sort of a minor thing. So here's the proof of our baby residue theorem. So we're going to go around to each of these poles and let Pj of z be the principal part of f at zj. So recall this was where you just pull out the finite sum of the terms of this form, so just z minus zj to a negative power. So here's what they look like. Pj, I'll have the residue times 1 over z minus zj by definition of the residue, and then plus these other possible negative powers of z minus zj. So you do this at all of the different poles, but there are finitely many. And as we saw in proving partial fractions decompositions for rational functions, I can take f and subtract away all of the principal parts, and I'll get a function that's analytic on the closed disk. So then I'll get that the integral of this analytic function dw on this circle of radius r is 0, and that's so that comes from the Cauchy integral formula. We've mentioned it before, that if just f is analytic in dr and I do just the integral of f itself, I'll get 0. Okay, so now that this is 0, we get that I can compute the integral of f. So we're in the case where f is not analytic, it has these poles, but we're accounting for that with the principal parts. So we get that this is the sum from 1 to n of the same integrals here. And now each one of these principal parts, remember, was written above. So it has this first term and then these other terms. And so if we try to integrate these on this circle, well, we'll just use the lemma above. If I can put it here. The only term that will matter is the one that occurs when I have 1 over z minus zj. So out of this, you get the sum of the residues. Because only this first term will matter, because these other terms, I'll get 0 in the integral, and so I'll just be peeling off the coefficient, which is the residue. And that proves this simple version of the residue theorem. And so the answer to the question, why was the complex analyst dog named Cauchy? Because he left a residue at every pole.